I'm Kieran from CryptoBulls. Really happy to have you here with me today. So we'll be talking about Vitalik Buterin's new post around the topic of Ethereum scalability. So if that's something that interests you, then stick around because I'm going to try and break down his latest post that he published on his blog Vitalik.ca, and it's the dawn of hybrid layer 2 protocols. Now, these protocols can hopefully become a solution to Ethereum's scalability problem, and in this video I'll try and do my best to explain different terms, different approaches, explaining what Plasma protocol is, what state channels are, what benefits hybrid layer 2 protocols can bring to Ethereum, and yeah, more or less that. And all the articles and videos will be added in the description below, so if you have always wanted to know this, get a bit of insight on how Ethereum scalability issues are being addressed right now, what approaches are being used, then this video is for you. So sit back and relax, and I'll try and break it down as best as I can. Now, I copied the whole article and put it in Google Docs so I can add some notations and so on, and hopefully break everything down to make it a bit more digestible, as it's not an easy article to go to read. Now, first and foremost, the current approaches to layer 2 scaling are, maybe you've heard of Plasma and state channels and you're still not 100% sure what they are, and I found some interesting graphics here that hopefully explain. So we'll start with Plasma. What is Plasma? Now, it's a very interesting concept, and it dates back to around 2017, and it was used as a scaling solution technique for the Ethereum blockchain. Now, the idea of the Ethereum Plasma is basically to establish a framework of sidechains. Now here you've got an example. Here you've got the Ethereum blockchain, and underneath of the Ethereum blockchain you've got now two child blockchains, and these will be the sidechains, and these sidechains each have again two other sidechains. And the idea, so if we use the Ethereum blockchain as an example, such a framework is designed to help and operate as a blockchain tree. So it looks like a tree with its branches and these numerous smaller chains which are created below the main one, and these smaller chains are also referred to as plasma chains or child chains, and help increase the transaction speed and scalability of the blockchain. Now, here there's another one. So instead of one central blockchain, they're split into two different child blockchains, and these child blockchains can communicate with the original blockchain, and you can merge these child blockchains into one central chain. And by having so many different child chains, you can increase. So for example, if you've got 4 different child blockchains, this would lead to a 4 times increase of the main blockchain, and that's one way to address the scalability issue. So what are state channels? So first of all, state channels refer to the process which users transact with one another directly outside of the blockchain. So basically they're transacting off-chain, and this greatly minimizes the use of on-chain operations, so it prevents clogging up the network. And it's a very exciting aspect of the Ethereum scaling solution. And you can compare state channels with, for example, Bitcoin's Lightning Network, but instead of only supporting payments, they also support state updates, so you can use it for a voting system as an example. So even though there's these very good approaches to improve Ethereum scaling, such as Plasma and state channels, there are some very big challenges in both, and I think it's important here to realize what made Ethereum popular at the beginning. And the thing is, one big reason that Ethereum became popular is the very easy developer experience you had. So you could write a program, publish a program, and anyone could interact with it. Now, the problem with designing a state channel or a Plasma application is that it relies on very explicit reasoning about incentives and application-specific development complexities. So it works really well with specific application use cases, for example, with Seller is actually a platform that allows two-player games between two parties. Here's the website. And it's the most advanced layer 2 scaling platform, and it's very interesting indeed. Seller Network is a leading two-player scaling platform that enables fast and easy, secure off-chain transactions for not only payment transactions, but also generalized off-chain smart contracts. And you can develop two-player games on this application, and that's very interesting. So I suggest that you check this out and look at Seller. You can develop games on Seller with the SDK. So very interesting. You can monetize your HTML5 games with just 2 lines of code as an example. So very interesting. And that's an example of a state channel use case. So let's go back to the article. Now, the thing is here with Plasma. Now, Plasma, for instance, Plasma Cash can work well with payments, but using it in a general use case is very difficult, and the big challenges are the amount of data history that is saved. So Ethereum style smart contracts on Plasma seem extremely difficult, and that's because of the amount of data history that is used. So using Plasma on an exchange would be very difficult. So here Vitalik starts talking about a new forgotten category of semi-layer 2 protocols, and there was a blog post back in 2014 which introduced the idea of shadow change. And the interesting part here is that here the block data is published on-chain, but blocks are not verified by default, and this is actually a very interesting approach. So the thing here is, even though the block data is not verified by default, if there's something wrong with the block, as far as I understood, the block can be challenged. And here it states, if the block proves to be invalid, then chain from that block is reverted. So now the interesting part here is the contract does not keep track of the full state of the system. It only keeps track of the state root. And yeah, at first I wasn't 100% sure what the state root is. And basically, Ethereum, unlike Bitcoin, has different properties that every block contains something called the state root. So the state root has a lot of information, including account balances, contract storage, contract code, and account nonces are inside this state root. So this is very, very important. And basically, the contract just keeps track of the state root and manages to validate if this block is correct or not. Now, there's also the ZK zero knowledge rollup, and this is more or less the same thing, but it doesn't challenge period. So basically what it does is got a ZK rollup contract, and it uses technology called SNARK, and basically this cryptographic proof checks the previous state and the next state with deltas. And deltas, if I'm explaining this correctly, is it more or less represents the difference between randomness on the other side of the equation. And yeah, I probably mutilated that description. I'll link a article below which better explains what deltas are and how SNARK calculations work. And I'm pretty sure that can explain it a lot better than me. So I'll link that down below. But basically, it's zero knowledge rollups using zero knowledge SNARKs to verify the block's validity by using these state contracts. So in both cases, the main chain is used to verify data availability, but not to directly verify block validity or perform any significant computation. So this is the big problem with zero knowledge rollup is that there's a lot of data, and this on-chain data overhead will create a bottleneck. However, the idea here behind this is that it's not such a bad issue because data is cheaper and than computational power, and this data can be compressed to a certain extent. Now, scalability gains that zero knowledge rollup can bring is around 500 transactions per second. That's around a 30 times gain over the current Ethereum TPS at the moment. Now, one thing that's pretty interesting is there's the upcoming Istanbul fork, and this will reduce the gas cost of data from 68 per byte to 16 per byte. And that's a 4 times increase. So with the already 30x increase that we have thanks to zero knowledge rollup, which promises a 500 transaction per second, we would have a 4 times of that. So that would mean when using zero knowledge rollup and the next Istanbul hard fork, we would have around 2,000 transactions per second, which is a lot. That's a lot. That's a 120x gain from the current TPS that Ethereum has, and I think that's a very fantastic increase in transactions per second. So, what are the benefits of data on-chain techniques such as zero knowledge optimistic rollup versus data off-chain techniques such as plasma? Now, first of all, there's no need for a semi-trusted operator, and I'll explain to you why in a moment. So first of all, now on-site chains, you need semi-trusted operators, but with the zero-knowledge optimistic rollup, a malicious actor, you can actually publish a bad block and it will automatically be challenged by the next submitter. And I think this is very good because he can calculate the internal state with, first of all, cryptographic proof using the state rule and the data to check the validity of the block and make sure that it's valid and not a bad block. Now, that's basically what we looked at before with this table here, with the state deltas here on the left. And basically, these state deltas is information that is sufficient to allow anyone to independently calculate the full updated state tree and make sure that it's correct. And on the right side here with the previous state and the current state and the cryptographic proof that proves that the previous state has a state root and so on. Very good. And that basically means that you can have a permissionless operator. And the only thing that you need then is, if you want to become an operator, is pay 10 Ethereum, and then you can become a permissionless operator. Now, one downside to the zero knowledge optimistic rollup is, in theory, it's generalizable, but in practice, it's not easy to create generalizable use cases with zero knowledge rollup. And it is the purpose computation. The reason why is the computations are very difficult to do at the moment. And it's maybe possible with maybe the Ethereum virtual machine, but still, at the moment it's very difficult. Now, the third thing is optimistic rollup is much easier to build for clients because it's very specific and there's no need for a second layer networking. You can just scan the blockchain. Now, if we look at where the advantages come from for optimistic rollup, I think here, a side note, I think it would be very good if you look at Vitalik Buterin's video because he explains the problem, the very complex problem of data availability problem in the video, and the link is down below. And here he goes over how there are basically 2 ways to cheat in a layer 2 system. The first way will be with invalid data to the blockchain, and the second data is with unavailable data. Now, it's very easy to deal with invalid data because the submitter can be heavily penalized, but with unavailable data becomes very harder to deal with because even though there's this unavailability, it can be detected when the submitter challenges it. It's very difficult to determine whose fault it is for this non-publication, and also then penalizing that submitter that didn't publish the data. So that makes it very difficult. And this whole problem is very well explained with the Fisherman's Dilemma. And as a side note, Vitalik Buterin actually posted a video talking about that, which is the one that we were talking about here before with the data availability problem. So he also goes over the Fisherman's Dilemma and talks about the 2 ways that you can cheat in the system, and also shows how problematic that can be. Now, here we've got nice image with the Fisherman's Dilemma, and here it's highlighted the two problems that we've got. So first of all, in case one, we've got the issue that V1 publishes block data with missing data. So that would be the unavailable data. Now V2 raises an alarm, and T3 here in block 3, V1 publishes the remaining data. And in case 2, here you've got the case where V1 publishes all the data and V2 is a malicious actor, and he makes a malicious challenge even though the data is still there, and that is a big problem. So now that we've seen one of the big disadvantages of a zero-knowledge optimistic rollup with the Fisherman's Dilemma, the thing is if we go back to Plasma and state channels, they both work around this dilemma by pushing the problem to users and making it the user's responsibility to exit and move to a different operator. And basically, as a user, you have the responsibility to check the data and all the transactions you signed, and that allows you to prove the chain and the assets that you held inside the layer 2 protocol, because you're the only one that has the signature to prove that these assets are yours and not someone else's, so you get the assets. Now, this solution is indeed very elegant, but it relies on the fact that every state object has an owner. So this means that it works for unspent transaction output-based payments, so basically cash payments, digital cash payments. But it does not work so well with account-based payments, and also with different applications. For example, Uniswap, that doesn't have a natural owner. And even those applications that do, there's often multiple people that can make edits to the object, and that's problematic. There are also other issues specifically to Plasma and channels individual. And first of all, channels do not allow off-chain transactions to users, and are they part of the channel? That's a big problem, because basically that's the whole idea of peer-to-peer payments, that you can just send money to anyone. But if they're not in your channel, you cannot just send them a new transaction. Now here the big problem is, for example, if you take the $1 from one user sent, basically this user could send $1 to many different users using state channels, and could basically be doing a double spend on multiple state channels. And the way to go around that, Plasma uses a very big transaction history which prevents this double spending, and that's one big downside to Plasma, that has such a big data history that clogs up the network. So now, because of this data on-chain computation off-chain layer 2 techniques, they don't have the data availability issues, and zero knowledge and optimistic rollup make sure to have enough data on chain to calculate the layer 2. So in short, this ensures the replacement of the missing participants. Now we've seen some advantages and disadvantages of Plasma, state channels, zero knowledge, optimistic rollup, and so on. And we've seen what kind of benefits in the scalability area they can bring for the Ethereum blockchain. But what if developers and users want even more scalability? What options are there here? So basically, in short, more scalability can be achieved by, first of all, reducing the data history of Plasma, because that's very big, and maybe creating a map between matched orders between the history, and that can be reduced to a very small amount, to around 4 bytes per order. So the idea here is combining the technologies of optimistic zero knowledge, optimistic rollup, Plasma, state challenge, and so on, and being able to create a hybrid layer 2 protocol. And I think the direction is also going to be that more of the data is going to be published on chain, at least for some time, which of course helps and eases development and helps the general use case, increases security, and uses the per user load, which is very important. So if you want to read some more information on this, Vitalik also put some links below talking about introducing the OVM, a blog post by Carl Floersch, and related ideas by John Adler. So if you want to read those, you can go to Vitalik Buterin's post that I linked down below in the description. So I hope you enjoyed this video. I know this was a bit more technical than I wanted, but I hope I managed to break down some aspects of the scalability issues, what's been done to improve this scalability. And I like the road that Ethereum developers are taking, and I also appreciate all the work that they're doing to improve Ethereum. So if you enjoyed this video, then I'd appreciate a subscription, and if you want to stay up to date and get similar type of videos, then hit that notification bell to stay up to date. And if you've got any suggestions, any feedback, I'm greatly appreciative of any type of feedback that I get in order to improve the videos, in order to get some other topics to talk about. If you want me to discuss certain topics, then put it down in the comments below. So without further ado, I wish you a fantastic day and start to the week, and I'll see you on the next one. Bye-bye.